Well, I mean, let's be fair. They don't really get views or anything. You know, like SPI, the people who try to show for them, they're not exactly popular creators. Let's just be honest here. By the way, this file.
Waiting for the audio. Okay. Who's that? Common Man Show?
अगर बाबू आपको याद हो तो पहले हम स्पेसएक्स से संबंधित वीडियोस देख चुके हैं जिसमें हमने रॉकेट्स के लॉन्च भी देखे थे, अंतरिक्ष यात्री भी देखे.
Why Israel can't defeat Hezbollah?
The resistance and starve the resistance, and this is why the Israelis trying to get rid of all the Palestinians in North Gaza. Now, Anas al-Sharif, the Al Jazeera journalist in Gaza, who recently actually was accused of being either Hamas or Palestinian Islamic Jihad. The Cradle covered this, but Israel recently came out and called claimed that they had documents showing that 5 journalists, Al Jazeera journalists, are either members of Hamas or the Palestinian Islamic Jihad, similar, of course, to what they did with the allegations against UNRWA. But as we know, they've been targeting journalists relentlessly in Gaza, and this has led to over 180 journalists killed. So Anas al-Sharif, who is there now, along with a few other journalists, posted a tweet yesterday saying, what is happening, the scene now in northern Gaza, because I got to amplify his voice because I'm not there. Burning schools and shelters, so setting them on fire, burning houses with families inside, destroying residential neighborhoods over the heads of children and women, blowing up entire residential blocks, artillery shelling of civilians, and shooting anyone who moves, siege, starvation, thirst, extermination, storming, and displacement.
I'll gladly debate. I'll debate you guys. So I already left them a message. I'll gladly debate you guys.
Michael Faraday had a concept that explained the dynamics of the electric field. He used tubes, and these Faraday tubes is what this video is about. To give a deeper understanding, we need to understand the concept of these lines of force by making use of Faraday tubes. J.J. Thomson, in his book Electricity and Matter, explains this into detail in the first chapters of his book. And I will explain it to you in this video. Enjoy. Michael Faraday, a great researcher, had the concept that the whole field of electricity was filled with lines of force, and that it had a fibrous structure, like a bundle of hay or straw. And to Faraday, this concept was a reality, and he gave physical properties to these lines of force, to these Faraday tubes. In this video, I will use straw.
Yeah, to him it was real, and to you, what is it? It's not real? I don't understand these people. Like, the ancient ones, they used to... Wait, are we streaming? Did we do an audio? Yeah. Yeah, those ancient idiots like Faraday, what did they know? They thought electricity was real. Now we know it's not. Yeah. Okay. Makes total sense.
To visualize some of these properties. Now, this straw is inflexible, but in reality, these straws are elastic. You can stretch them up, and they give tension. Another property of these Faraday tubes is they repel each other. So if you have a bundle of them, they want to get away from each other. First, we're going to take a look at 2 charged particles, one positive and one negative. So they attract. And what causes this attraction are these Faraday tubes, because they represent tension. Like an elastic band that is stretched, it wants to stretch back. And this tension is what pulls together the...
But we know that this is caused by photons. We know that there is a boson gauge symmetry. There is particle exchange. There are particles being exchanged. Otherwise, why are 2 electrons moving away from each other? This is what we know today. I mean, we know there's actual particles in there.
Particles. Figure 2 shows two particles A and B, and they are oppositely charged. A is positive and B is negative. Between them and around them, you see the lines of force represented by the Faraday tubes. And as you can see, between A and B, most lines are concentrated. Now, as these tubes have tension, A and B are pulled together by having more tension between them than on the opposite sides of them. Left of A and right of B are less lines of force, less Faraday tubes, less tension. And between A and B are the Faraday tubes concentrated, so there is more tension between them. And this difference in tension causes them to be attracted to each other. We have now looked at attraction of opposite charged particles. But now we are going to take a look at equally charged particles, positive or negative, both. They repel each other. Now, why is that? Again, this is explained by making...
This is very interesting. This is basically a quantum mechanical explanation for attraction. Wait, what did he say?
And right of B are less lines of force, less Faraday tubes, less tension. And between A and B are the Faraday tubes concentrated, so there is more tension between them. And this difference in tension causes them to be attracted to each other. We have now looked at attraction of opposite charged particles. But now we are going to take a look at equally charged particles, positive or negative, both. They repel each other. Now, why is that? Again, this is explained by making use of Faraday tubes and the tension they represent. Let's take a look. Figure 3 shows two particles that are equally charged, so they're both positive. A is positive and B is positive. These Faraday tubes are always terminated on conductors. One end represents the positive charge and the other end represents the negative charge. So if A and B are equally charged, there won't be a Faraday tube between them. As the charge is equal, there won't be any tension. Instead, the dielectric lines of force, the Faraday tubes, are terminated on objects in the field around the particles, in conductors around the particles representing the negative charge. And because these lines are now concentrated outside of the region between A and B, because these lines are pushed apart, they are pushed sideways because they don't like to be together. So you can see between A and B, there are no lines of force, there are no Faraday tubes. And instead of being pushed out of each other, you can now understand that it isn't a pushing, but a pulling. The Faraday tubes are pulling away A and B from each other by being connected to the outside negatively charged particles of conducting material. So it is not a pushing away, but a pulling away. The same action of pulling toward each other is now pulling them away from each other. We have now got the concept of tension and the pull it represents on a particle. Now let's step into another example, the example of a capacitor. A capacitor has two plates, very close together, and in between is a dielectric medium. And in this dielectric medium is set up a dielectric field when the plates are oppositely charged. So one plate is positive, the other is negative, and in between is set up the dielectric field made up of these Faraday tubes. These tubes represent tension, so they actually pull the plates together. And they repel each other. So when we have a bundle of them between the capacitor plates, they want to get out. And if we make a short loop, a shortcut between the plates, they will be pushed out because with a shortcut, these Faraday tubes are drawn into the molecular structure of the copper, of the conductor. Let's take a look at this. Figure 5 shows plate A and plate B being positive and negatively charged. In between is set up a dielectric field made up of Faraday tubes. And PQ is one of these Faraday tubes. If we now connect to this plate a shortcut, a wire of A, F, G, then these Faraday tubes will be pushed into that line because they repel each other. So they are pushed away from each other, sideways, transversely, into the wire of E, F, G. These Faraday tubes...
Okay, I don't know. I'm not getting a picture of what he's talking about. And I'm beginning to fall asleep. Wait, Science is Silent has a new video?
You've said before, when trying to animate something for a quantum video, something is going to be wrong about it.
Yep.
You can't actually make it correct because we can't see it.
I don't think that we should be trying to come up with pictures. This is abstract mathematics.
Right.
But I gotta give the
That is so ridiculous.
people what they want.
People demand pictures.
What do you know about quantum spin?
Quantum spin. It is a quantum property. Oh, man.
Trying to come up with pictures. This is abstract mathematics.
Right.
But I gotta give the people what they want.
People demand pictures.
What do you know about quantum spin?
Physicist analogy hater.
Quantum spin. It is a quantum property. Oh, man. It's got to be different for reasons amongst the different particles. I don't know. I think that's about it.
So not much, I'm
No,
gathering.
no. Oh, something about fermions.
Yes.
That? Yeah.
Yes. We'll get to that later.
Okay.
Even by the end of the 1920s, early 30s, this new quantum field theory starts to develop, where particles weren't really particles, they were just, excitations in quantum fields,
It might
right?
not even be there at all. I'm just kidding. It's not what it is at all.
When?
Starts to develop, where even by the end of the 1920s, early 30s, this new quantum field theory starts to develop, where particles weren't really particles, they were just, excitations in quantum fields,
It
right?
might not even be there at all. I'm just kidding. It's not what it is at all, but it feels like that sometimes.
Which we have another conversation video about.
I don't even remember that one.
The reason we call them fields is because they are properties or values assigned to points in space. So for example, if you have a spin 0 particle, you would have something we refer to as a scalar, a plain old number attached to every point in space.
Okay.
It's like the most basic quantum field you can make. Something like a photon is a spin 1 particle. In order to describe photons using quantum fields, you assign a vector to every point in space, an arrow.
Okay.
Don't think about it too much. Your brain will melt.
Well, I'm already starting to like shove
Yeah.
it back in.
For something like a spin 2 particle, we would assign a matrix or something. Things get more
An
complicated.
extra dimension.
Yeah. Spin 1/2 particles are tricky. They are described by something called a spinner.
I've never heard of a spinner.
Most people don't hear about it. It's not something that comes up in like the pop sci. You don't talk about spinners. It's a very mathematical thing.
Okay.
But something like an electron, which is a spin 1/2 particle,
Mhm.
its field would be made up of spinners.
A spinner for every point in space.
Yes, exactly.
Okay.
I'm going to attempt to make it more tangible today, and we're going to see where it does and doesn't work.
Sure.
We're going to use gears like this, and I'll have a better graphic on the screen, but what I want you to imagine is that the yellow gear is physical space. This is how a particle is oriented in real actual space. If we could actually see it and it was a ball, it's not. But if we could actually see it and it was a ball, this would be its orientation.
Okay. Mhm.
The larger gear is what we would call the state space.
Okay.
It is the quantum spin state of the particle. Those two things are connected, just like these gears are connected.
So is that like it's plus or minus?
We're only worried about the general 1/2.
Okay, so this
Okay.
is telling us it's 1/2.
Just an analogy.
Yeah.
But we're looking at a spin 1/2 particle here. It has physical space
Mhm.
and a spin state. Two different things that are connected to each other.
It has an orientation telling us where it is in the universe,
Yes.
and that's the physical location.
Right.
And then it has another, what did you call it?
The quantum spin state.
State. It has another state that is how the spin is oriented.
How the spin is oriented in an abstract quantum space,
Mhm.
not the real space,
Mhm.
mathematical space.
Yep.
And I'm going to just take this one electron and I'm going to rotate it around 360 degrees. Now we can take a look at the state space, the spin
Mhm.
state. Is it the same as it was before?
No.
No, it's not.
It's opposite.
There appears to be a little more rotational freedom within this spin state space. Now, if I rotate it around another 360 degrees, we get back to where we started.
Mhm.
We have to go around 720 degrees before it gets back.
Okay.
It's a circle with 720 degrees in it.
Interesting.
This is an analogy, right? It's something that takes one aspect of a spinner and shows it visually. It doesn't show them all. There's no way for us to like operate with gears, right? We can't extend this and be like, oh, it's just gears. It's
Gears all the way down.
gears all the way down. It doesn't work that way.
Steampunk has finally had its moment.
So I have another analogy for you.
Okay.
And this one was actually developed by Paul Dirac. It's called the Dirac belt trick.
Oh, all right.
Forget about particles for a second.
Okay. Mhm.
What I want you to do is I want you to hold this end of the belt.
Mhm.
We talked about the gear we're having to rotate by 720 degrees to get back to where it started.
Yeah.
So what I'm going to do is I'm going to take these and I'm going to rotate it 180, 360, 720. Okay.
Yeah.
So now we have a belt that is twisted 720 degrees.
Okay.
And I want to show you that this is the same thing as the way we started.
Okay.
And so I'm not going to change the orientations of the two ends.
Mhm.
We're just going to go like this. And so it is the same.
Beautiful.
Okay.
That's exciting.
Right. The belt had two ends,
Mhm.
right? Imagine you've got that cube as an electron and the cube is rotating and it's connected to the grander universe with a Dirac belt
Okay.
on each of its sides.
Uh-huh.
As this thing rotates, you expect it to get all twisted up,
You do.
but it doesn't.
I kind of hate that it doesn't.
Right.
It's confusing.
But again, it's just an analogy, so it kind of falls short.
Sure. You've said before, when trying to animate something for a quantum video, something is going to be wrong about it.
Yep.
You can't actually make it correct because we can't see it. Making an illustration of it is then applying properties to it that don't exist.
I don't think that we should be trying to come up with pictures. This is abstract mathematics.
Right.
But that certainly doesn't stop other people from trying.
And you, frankly.
And me. Well, I mean, I have to make a living.
Yeah.
I gotta get the people what they want.
People demand pictures.
People demand pictures, and so I've got to try. But then I have to like also make sure that I say, well, it kind of works for these couple of things about it,
Yeah.
and then this other picture kind of works for these other things about it,
Yeah.
and that's kind of the best we can do.
Mhm.
You can kind of think of spin as describing the way that a particle is connected to the universe as a whole.
Okay.
And I mean, that's what the analogies were telling us. For the gears, a 720 degree rotation in physical space always corresponded to a 360 degree rotation in the quantum state space.
Right.
And for the belt, 720 degrees worth of twists was equivalent to the starting state of the belt. And when we use multiple belts, we can see that connection. And so essentially, quantum spin tells us what that connection looks like. Spin 1/2 particles are connected to the universe differently than spin 1 particles.
Sure.
And so we end up with two major categories of particles.
Mhm.
We end up with fermions,
Which are spin 1/2.
spin 1/2 and spin 3 halves and spin 5 halves and 7 halves and 9 halves, all the halvesies. Then we have the other category, which are the bosons. And they are spin 0, spin 1, spin 2, spin 3, and so on.
The integers.
The integers. And something we've noticed is that the halvesies particles, the fermions, behave in different ways. They obey different statistics.
It makes sense.
Well, if the spin is how it's connected to the universe, obviously the halvesy ones are going to be connected differently than the holes.
Which is going to affect the way they behave.
Right.
Sure.
This relationship that spin has with statistics,
Mhm.
we aptly named the spin statistics theorem.
I am comfortable with that.
Yes.
Creative.
Right. Unfortunately, we don't have a proof for it.
So they're just hypothetical?
No, we see it.
Experimental.
We see it experimentally.
But you haven't figured it out theoretically.
Right. We don't have a theoretical proof
Okay.
for it. We have experimental evidence, piles of it, right?
Piles of it, yeah.
Everyone is like, the theory is right
Mhm.
because the universe is telling us so.
Yeah.
But we can't figure out exactly why theoretically. I think Wolfgang Pauli had the most realistic perspective. We use it because it works.
Succinct.
Right.
Straight to the point.
Yes.
I like it. So we make it to the end. Ugh.
How's your brain doing?
You know, I think that it's mostly still intact. I think I made it.
Okay, that's great.
Yeah.
That's great.
Miraculously.
But until next time, remember,
It's okay to be a little crazy.
aren't neutron stars more dense than white dwarfs? Yes, they are. But fun fact, neutron stars are also made of degenerate matter. It's a wide category. Anyway, thanks for watching.
Wow, falling asleep. I'm so tired. That was a disaster. Oh my God. So in 14 minutes, he put me to sleep. Oh my God, I think I'm gonna go take a nap. Yeah, I'll go take a nap. Bye.